With each captivating picture caught by the James Webb Space Telescope, it keeps on gathering insights from various corners of the universe, including planets inside our own planetary framework. A year earlier, we marveled at some of its most significant images, such as the Ken Cloud, the Stephan Quintet, and, strikingly, the enchanting Profound Field picture. This sweeping image, in particular, depicts various galaxies resting within the immense size of the universe, answering questions that have been raised for a very long time. The James Webb Space Telescope has not ceased to be a maze of mystery. In fact, it has revealed objects that challenge deeply held cosmological theories. These surprising discoveries are now being referred to as universe breakers by cosmologists, frustrating established experts with their ability to challenge existing theories. The reasons behind these revelations remain shrouded in mystery, throwing our hypotheses into disarray. So, what's the latest scoop from the James Webb Space Telescope? What astounding new discovery has it revealed that was previously unknown to us? Join us as we dive into the revelations of how the James Webb Space Telescope has presented evidence suggesting the presence of another universe, challenging the standard understanding of the Big Bang. Our universe, as we've long understood, arose from a hotter, denser state through a theory known as the Hot Big Bang. This idea, a critical scientific achievement over the past few decades, gained overwhelming support in the 1960s with the definitive discovery of the cosmic microwave background, CMB, a remnant from the early hot and dense state. Over time, the Big Bang theory has remained the dominant explanation for the origins of our universe. However, recent key insights have prompted cosmologists and astrophysicists to reconsider both the ongoing development of the universe and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, with the prevailing view holding that the universe began as a smaller, denser entity in the distant past. The presence of radiation, such as photons, indicates that the universe was hotter at its inception and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels fluctuated, reaching a point where known laws of physics would break down, around 10^3 seconds after the supposed beginning. At such short timescales and high energy levels, our current understanding is challenged. If the universe started as hot and dense, it would have expanded and cooled, producing a vast number of particles and antiparticles, with excess particles being annihilated by radiation as temperatures dropped. The breakdown of the electroweak and Higgs forces led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles, such as quarks and gluons. The combination of protons and neutrons resulted in the formation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions underwent evolution due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. Nearly 380,000 years later, the discovery of the cosmic microwave background further solidified the Big Bang theory as the most widely supported explanation for the universe's creation. This theory describes the early universe as a hot, dense soup of subatomic particles that gradually cooled over time. While most cosmologists and astrophysicists embraced the Big Bang theory, firm supporters of the steady-state hypothesis, such as Fred Hoyle, continued to promote increasingly controversial ideas, only to face defeat in the face of overwhelming evidence. The presented evidence was decisive. It wasn't obscuring starlight or reflected heat from dust. The cosmic glow exhibited exceptional consistency, resembling a perfect black body, yet had no connection to known objects in the universe. Regardless, Hoyle and his colleagues continued to challenge scientific progress by advocating scientifically questionable ideas. Meanwhile, the fields of space science and cosmology underwent vast transformations from the 1960s through the 2000s, with cosmology making particularly significant strides. Scientists mapped the universe, described its large-scale structure, and studied the evolution, development, and interactions of galaxies and their cosmic populations. However, despite these advances, inconsistencies arose that challenged explanations within the framework of the Big Bang theory. Most notably, the absence of predicted relics, such as magnetic monopoles or particles from grand unification, led many to reconsider aspects of the theory. The universe we observe today appears to require forces beyond our current understanding. Despite these difficulties, the inflationary model and its challenges persist. While existing theories fail to account for observed anomalies, two approaches have emerged: refining current theories or considering alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang model. Inflation proposes a brief period of rapid expansion that smoothed the universe, giving it uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and shifts, supporting its validity. Nevertheless, despite alternative theories, inflation's scientific strength remains unparalleled. Roger Penrose's work, alongside his collaboration with Stephen Hawking, failed to match inflation's progress in explaining the universe's earliest moments. Recently, attempts have been made to undermine the validity of inflationary theory by supporting conformal cyclic cosmology. However, this theory is inherently flawed from a scientific standpoint. The key difference lies in their predictions. Conformal cyclic cosmology proposes that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflationary theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang time. Cosmologists quickly noticed anomalies in the images sent by the James Webb Space Telescope beginning in 2022. These discoveries may require a reassessment of key aspects of the universe's origins and evolution. One critical discovery made by the Webb telescope was the presence of fully developed galaxies much earlier than expected by the standard cosmological model. This phenomenon challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. These revelations disrupt our understanding, similar to encountering grandparents depicted as children in a story. Additionally, later evidence has revealed inconsistencies within major theories of the universe, such as the persistent discrepancy in determining the Hubble constant, which continues despite improvements in data accuracy and measurement techniques. New data from the Webb telescope presents challenges to the current cosmological model. These issues highlight flaws within the model, raising questions among scientists and physicists. While the model has undergone revisions in recent years to align with emerging data, some argue that these changes have been too accommodating. As a result, there is growing recognition that a paradigm shift may be necessary, possibly reshaping our understanding of the universe's fundamental properties. The Standard Model of Cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe in the 1920s. Subsequent discoveries have continued to build on this foundation, yet the latest findings from the James Webb Space Telescope suggest that we may need to rethink some of our most fundamental assumptions about the cosmos. For example, the location of enormous microwave background radiation in 1964 affirmed the hypothesis of the universe's origin as the most plausible explanation for its beginnings. This discovery described the early universe as a hot, dense soup of subatomic particles, continuously cooling over time. Achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. The possibility of infinite expansion, proposed in 1981, was suggested to resolve anomalies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theories. According to this model, the early universe underwent rapid expansion shortly after the Big Bang. While specific issues are addressed by this theory, new challenges arise, particularly given the prevailing belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Several notable anomalies, such as singularities within black holes, find support through indirect evidence. However, the groundbreaking discoveries of the James Webb Space Telescope regarding galaxy formation and ongoing issues with the Hubble constant raise concerns that we may be approaching a tipping point, where a significant revision of our current cosmological model becomes necessary. This could require a complete reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Unlike many other scientific fields, Cosmology deals with fundamental questions about the universe, its origins, and our place within it. The study of consciousness and quantum physics also explores similar themes, examining the intersection of theory and reality. It is crucial to reconsider these foundational assumptions, given the impact of theoretical presuppositions on data collection. History has shown that shifts in scientific thought, such as the transition from geocentrism to heliocentrism, or the discoveries of evolution and relativity, have led to profound changes in societal perspectives. A similar transformation in our understanding of the universe may be on the horizon, driven by an impending scientific revolution in cosmology. Scientist Robert Anton Wilson argues that theory becomes essential when further scientific inquiry fails to provide satisfactory answers. Investigations into cosmology may ultimately lead to the collapse of the current model, not due to observational errors, but because of its inability to incorporate new paradigms that fully reflect the latest discoveries. The prevailing narrative must therefore be reconsidered in light of new evidence. As the James Webb Space Telescope continues to unveil findings that could permanently alter our perception of the universe, renowned astrophysicist and science communicator Neil deGrasse Tyson has made headlines with his comments on its discoveries, particularly regarding the possibility of another universe. Launched in December 2021, the JWST is a powerful space telescope designed to explore the universe in infrared wavelengths, allowing scientists to see further into the cosmos than ever before. Tyson's remarks stem from the astonishing discoveries the JWST is already making, particularly in areas such as the formation of the earliest galaxies, stars, and exoplanets. While Tyson did not explicitly claim that the JWST has found evidence of a parallel universe, he alluded to some of the perplexing and unexplained phenomena observed by the telescope, which could point to something beyond our current understanding. One such anomaly is the presence of unusual, unexplained patterns in the distant universe. These findings suggest that the laws of physics as we know them may differ in other regions of the cosmos, or that the universe itself could be far more complex than previously imagined. This raises the possibility of multiple universes, as proposed by certain cosmological theories, such as the multiverse hypothesis. However, it is crucial to note that while these observations are intriguing, they do not yet provide concrete evidence of another universe. Rather, they open up new possibilities for theories and ideas that could redefine our understanding of space, time, and reality itself. As the JWST continues to probe deeper into the universe, it challenges the limits of current scientific knowledge and opens new avenues for discovery. While our understanding of space has long been constrained by technological limitations, the JWST's advanced capabilities provide an unprecedented view of distant stars, galaxies, and cosmic phenomena that were previously beyond reach. For instance, its ability to observe in the infrared spectrum has allowed scientists to peer through vast clouds of cosmic dust, revealing hidden details about star formation, galaxy evolution, and black hole behavior. These findings expose previously unknown dynamics and behaviors, adding layers of complexity to our understanding of the universe. A particularly intriguing aspect of the JWST's discoveries is its examination of galaxy formation. The detection of fully formed galaxies much earlier in the universe's history than previously thought has left cosmologists questioning standard models. The current paradigm, based on the Big Bang theory, suggests that galaxies took time to form, with stars and black holes initially emerging before coalescing into galaxies. However, JWST data appears to indicate that galaxies may have formed in a much shorter time frame, necessitating a significant reevaluation of our understanding of cosmic evolution. These discrepancies are not just fascinating. They challenge core assumptions about the speed and mechanisms of cosmic development. Further complicating current models are the strange patterns and fluctuations observed in the cosmic microwave background, CMB. Often considered a cornerstone of Big Bang cosmology, the CMB may be showing signs of irregularities that were never anticipated by traditional models. For example, questions have arisen about the uniformity of the CMB's temperature variations, with some observations suggesting that it may not be as smooth as previously believed. This could indicate unknown processes or forces at play, potentially leading to a major shift in how we perceive the early universe. In addition to galaxy formation, the JWST has also provided insights into the evolution of exoplanets. While the discovery of exoplanets is not new, the depth of information now available has increased dramatically. By analyzing the atmospheres of distant exoplanets, scientists can assess their composition, temperature, and potential habitability in far greater detail. This could eventually lead to the identification of planets with conditions suitable for life. The implications of such findings extend far beyond the search for extraterrestrial life. They raise questions about how life might emerge in environments different from Earth, and whether our current theories on the origins of life are too narrow. Another compelling area of research that the JWST is helping to explore is the behavior of supermassive black holes. These cosmic giants have long fascinated scientists due to their immense gravitational pull and ability to warp spacetime. Observations from the JWST are allowing for more detailed studies of how black holes interact with their surroundings, including the galaxies in which they reside. One of the most exciting possibilities is the role black holes may play in galaxy formation and evolution. Some evidence suggests that supermassive black holes are intricately linked to the development of galaxies. Understanding this relationship could provide crucial insights into the mechanics of the universe and help us better comprehend the forces driving cosmic evolution. Despite the numerous breakthroughs provided by the JWST, its greatest mystery may be its ability to challenge the very foundation of modern cosmology. As scientists continue to analyze its data, it is becoming increasingly clear that there are gaps in our understanding of the universe that cannot be easily explained by existing models. This has led to a growing recognition that a new framework may be needed to fully grasp the vastness and complexity of the cosmos. Such a paradigm shift could have profound implications for how we perceive space, time, and the fundamental laws governing the universe. The exploration of deep space via the JWST is not just about uncovering new data. It is also an investigation into the very limits of human understanding. As we peer further into the universe's past, we are confronted with questions that challenge our most basic assumptions. With each new discovery, we are pushed to rethink not only how the universe functions but also how we, as humans, fit into the grand scheme of existence. In this sense, the discoveries of the James Webb Space Telescope are not merely scientific breakthroughs, they are philosophical ones as well, urging us to reconsider our place in the universe and the very nature of reality itself.